All right, thanks so much. And thank you to the organizers for the invitation to speak here. I'm really happy to talk about this topic at this conference, at my favorite online conference. Let's just jump right in with our favorite counting sequence that we were just discussing, the Catalan numbers. And we really love Catalan numbers, mostly just because they count lots of things. So one of the things they count is standard Young tableau of 2 rows. So I have one there at the top of the screen. These are fillings of a partition shape where the rows and the columns are each strictly increasing, and each number from 1 up to however many boxes you have is there exactly once. So besides being lovely numbers to look at, they count lots of things. And so here are some of the things that Catalan numbers count. And one reason that we love Catalan numbers so much is because there are nice bijections between all of these objects. So let's just review a couple of them. So on the top left, we have a dict path. It's a path that doesn't go below the axis. And then on the right, we have order ideals of the type A root poset, or just a triangular poset if you prefer. And the bijection there is, oh wait, there we go. The bijection there is that full area squares underneath the dict path correspond to elements in our order ideal. And an order ideal is a subset of elements in this poset, such that if an element is in your poset, everything beneath it has to be in the poset, or in the order ideal as well. All right, and then we'll continue with the bijections. So if you label the up steps of your dict path and just count which ones they are and put all of those numbers in the top row of your tableau, and then put the rest of the numbers in the bottom row, you get a standard Young tableau. And then if you take those same numbers from the up steps and from the first row and put them around a circle, and then connect arcs such that they're non-crossing, you get a non-crossing matching, and those numbers from the first row end up being the smallest number in their pair. So there's one way to connect up all the arcs. So those are some nice Catalan bijections that we're familiar with or could figure out or have given to our students in the past. So let's just concentrate on 3 of these objects. My claim is that when you have objects that have a nice counting formula, you have nice bijections between them, the next question you should ask is a question about dynamics. So perhaps there's an action on one of your objects that's very obvious, like a rotation on your non-crossing matching, which gives you another non-crossing matching. Your question should be, what does this correspond to on the other objects? And if you're lucky, or if the world is beautiful and as it should be, these may even be actions that you already know. And so the answer turns out to be an action you already know on the middle object. So on the 2-row tableau, the answer is going to be promotion. And so promotion, some people like to define promotion in terms of jeu d'échecan, where you delete the 1, then you just start sliding things over, whatever makes sense, whatever is to the right or below, whichever one is smaller, slides into the empty square until you get to an outside corner. Fill that with a number bigger than all the numbers and then subtract 1. The way that I like to look at promotion is instead you should look at 1 and 2, and then 2 and 3, and then 3 and 4, etc., until you get to one that you can swap and get a valid tableau. So we're going to look at each pair of numbers, so that each of these is called a Bender-Knuth involution. Either you swap them or you don't. Do whatever makes sense. And so we'll move all the way through the tableau. And this is the same tableau that we got using the jeu d'échecan method. All right, so that's promotion. And so this was an observation of Dennis White, that promotion on 2-row rectangular standard Young tableau corresponds to rotation on the non-crossing matching, just using the normal bijection we already discussed. So that's a lovely visual explanation for why promotion of 2-row rectangular standard Young tableau has order n the number of boxes. It's because it's actually a rotation of something with n points around the boundary. And then this promotion also exhibits cyclic sieving because these non-crossing matchings exhibit cyclic sieving. And I'm not going to define cyclic sieving, but it's just something that's even better than an action having a certain order is it describes the orbit structure. So there will be some notes about cyclic sieving on the slides, but I'm not going to discuss it. So anyway, so there's promotion and rotation in this first example. So then we have these other objects, these order ideals. And the question is, well, what action is going on over here? Okay, and the answer is what's happening as we're doing these Bender-Knuth involutions, 1 and 2, 2 and 3, 3 and 4, is we're looking at adjacent steps on the dict path, and we're swapping them wherever possible. So when we get to this spot with the 4 and the 5, on the dict path, it's an up and then a down step because it's top row, bottom row, and we switch that to, we switch the rows, and so we switch the steps. And then what's happening on the level of the pose set is we are toggling things from left to right in our pose set. So you can see whenever something changes in the tableau, something changes in the order ideal. And it's kind of I picked kind of a bad example, but it's too late now. Things only came out of the order ideal, but things could also get toggled into an order ideal. All right, so that's what happens on the level of this order ideal. And let's just call that toggle promotion because it matches up with promotion on this standard Young tableau. And it's beautiful. I mean, we filled out all the arrows, but there's one slight problem, and that is that toggle promotion isn't really an intrinsic action on order ideals. Because order ideals don't always have like a left to right. So I'm wondering, can we put something better in that spot? And the answer is that we can. And so this, excuse me, this action is called Rowmotion. So here is a well-defined action on order ideals of any pose set. You take an order ideal, you look for the minimal elements of the pose set that are not in the order ideal, and you let those generate a new order ideal. So you just take everything underneath those elements. We saw a beautiful talk by Peter Cameron yesterday. And what I have to say here relates to some of his prior work with Dima van der Vlas, in which they identified the toggle group as a really important permutation group related to order ideals. And they showed that Rowmotion can also be computed by toggling all your elements from top to bottom. So what I previously showed you was toggling sort of from left to right. And by toggling, I just mean for each element, you're either going to try to add it if it's not there, or take it away if it is there, as long as that makes sense and that gives you a valid order ideal. So now that Rowmotion is a toggle group action, we can use the structure of the toggle group to relate it to other compositions of toggles. So in particular, toggling top to bottom is going to be a conjugate element in the toggle group to toggling left to right. And that's something Nathan Williams and I showed about 10 years ago. And that ends up being exactly what we need to relate this action to something that's been previously studied, namely Rowmotion. And while we're on this slide, I did want to mention there's more than just top to bottom and left to right that are conjugate elements in the toggle group. Say you take your pose set, if you embed it in the n-dimensional lattice, you actually can toggle by like 2 to the n different sorts of hyperplanes and get actions that are conjugate to each other. And this will come up a little bit later in the talk. But in all of these situations, the point is an equivariant bijection is one in which the orbit structure is preserved. So we can say that we know something about the orbit structure of Rowmotion because it's conjugate to toggle promotion, which is equivariant with promotion and with rotation. So we can map all the way back to this rotation from Rowmotion on order ideals in this pose set, recovering a result of Armstrong, Stump, and Thomas that they proved on Rowmotion directly. All right, so we have this pretty picture with 3 of our title elements, Rowmotion, promotion, and rotation, that are all that all work together on these objects that are in bijection with each other. So let's talk about our 4th thing in our title, which was webs. So in this 2-row tableau and non-crossing matching case, the non-crossing matchings can be seen as SL2 webs, meaning we can associate to each non-crossing matching a polynomial in 2 sets of variables that's invariant under the action of SL2, which basically just means it's composed of 2 by 2 minors, basically right here. So in this example, this is the polynomial that is associated to this non-crossing matching. And you'll see that we're just taking each arc, like say this 2, 9 arc, is determining this little 2 by 2 minor with the indices 2 and 9. And so this polynomial, the theorem is that a basis for the spec module, which if you know what that is, that means something to you. If not, just think of the space of SL2 invariant polynomials. So a basis for that is given by all the polynomials associated with non-crossing matchings. And one great thing about this basis is that the long cycle acts by just rotating your diagram, and that's just going to rotate all of your indices on your variables. So rotation takes basis elements to basis elements, which isn't true of some of the other bases of this space. And then one other great thing is basically all these polynomials you can represent as matchings where there are crossings. And there are nice polynomial rules to resolve those crossings. So for example, here's a crossing, and you end up just summing the polynomials associated to the two ways to uncross it. So anyway, here's like a theory of webs. And the idea is there are diagrams associated to polynomials that behave nicely. All right, so now we have row motion, promotion, and web rotation. And now the question is this just a phenomenon for a two-row tableau, or can we generalize this to other areas? And so at the end of the talk, I'm going to show you one more example where we have all four of these things: row motion, promotion, rotation, and webs. But in the middle of the talk, I'd like to discuss a few situations in which we have some of these. And it would be really nice to fill out the whole picture and get all four things, though I'm not quite sure how possible that is in some of these situations, but we'll see a lot of examples. So the first thing I want to mention is that in other talks, I've talked a lot about more general realms where promotion and row motion correspond. So I'm not going to talk about most of that stuff, but there is some interesting recent work with Bernstein and Borland, especially where we generalize order ideals. Well, first you generalize to increasing labelings, and then to something called p-strict labelings, which is sort of like a generalized semi-standard tableau. So we get lots of interesting correspondences where the thing on the left of the arrow under promotion corresponds to the thing on the right of the arrow under some form of row motion, some of which ends up being sort of a higher level row motion, not just on order ideals. Okay, but I'd be happy to talk about any of that stuff if anyone is interested. But for this talk, I thought that it would be fun to concentrate a little bit more on these arrows over here. What are some situations where promotion corresponds to rotation, and maybe we also have some webs? Okay, so a natural first extension of this is, suppose we take our rectangular tableau from 2 rows and turn it into 3 rows. What can we say about that? Well, in work of Peterson, Pawlowski, and Rhodes in 2009, they had a correspondence between these standard young tableau and webs. And these are called SL3 webs. They're bipartite graphs. The interior vertices are trivalent. I'm not going to tell you like the precise definition. There's just a couple other things, but basically they look like this. They're really nice graphs. They actually are playbit graphs also. And notice all of the boundary vertices have the same filling in the bipartition. And all the web stuff works here too. There's like polynomials, they're invariant under SL3. So it's a very nice situation. The long cycle acts by rotation. But something that I just thought about when preparing for this talk was I don't really know a poset whose order ideals are counted by the same sequence as standard young tableau of 3 rows. So it would be really nice to be able to have a picture like this where we know some sort of poset whose order ideals are in bijection with 3-row standard young tableau, and such that row motion corresponds to promotion and such. Okay, so I'll leave that as an open question. I haven't thought about it too much, but I think it might be, I don't know, it would be really neat to see. And then another question here is, well, okay, there's some words there for the experts about webs, but the main question is, what about more rows, more than 3 rows? So in general, it's known that promotion has a nice order for rectangular shapes and even cyclic sieving, but we don't have a diagrammatic web basis for the spec module that rotates in the way that we want it to, so that you can actually see the rotation. Okay, so that's a really intriguing open problem. Here are some other instances where we have promotion and rotation. So here is a picture from Rebecca Patrias's paper on generalized oscillating tableau. So for a generalized oscillating tableau of 3 rows, that's going to correspond to rotation of SL3 webs, where now the boundary vertices can be of both colors. And Becky actually just told me there's some important work by Heather Russell that also is relevant to this situation. So that didn't make it on the slide, but I wanted to mention that. All right, so generalized oscillating tableau. Also, there's some interesting recent work of Chris Fraser, where he looks at D by 2 standard Young tableau. So now 2 columns and as many rows as you want. And that corresponds to rotation of certain SLD webs, where N is 2D. And you have all boundary vertices of one color. Now, this is a picture from Chris's paper, and the boundary vertices are of different colors, but that's just related to his construction of the bijection. They're all filled in vertices, and so that's what I mean by of one color. But yeah, that's a really pretty construction that I recommend reading about. And then here's something else. So basically that's what's known, 3-row rectangles and 2-column rectangles. And right now, joint work in progress with Christian Getz, Oliver Pachenik, Stefan Pfaffner, and Josh Swanson, we've been working on the 4-row case. So we have a really good candidate for some diagrams that rotate in the same way as promotion on 4-row standard Young tableau. And they end up being equivalence classes. And I'm just going to call them SL4 web-like diagrams. I think they are actually webs, but we have sort of 2 different ways to look at them. And this is more the web-like diagram. And one really interesting thing about this is that my absolute favorite combinatorial objects kind of popped up in this investigation, sort of out of nowhere. Namely, if you look at these different vertices in here, you end up with some regions in your web-like diagram that are actually configurations of the 6-vertex model of statistical mechanics, or in other words, alternating sign matrices show up in this construction. So we have basically some moves you can do on these graphs, and they correspond to the same moves you would be able to do on alternating sign matrices, or say like walking along the edges of the alternating sign matrix polytope. So anyway, we found alternating sign matrices in this project where we weren't even looking for them. So I would love to say more about this, but we do need to still write down the details. So yeah, great questions. Does it, how does gyration relate to this? Yeah, I'd have to think about that a little bit. But yeah, there's a lot more implications that will come from this. So give us a few months. We'd love to talk to you about it more in the future, but I wanted to put up this picture because anyway, it's very cool. I'm excited about it. All right, so that kind of ends the promotion and rotation section of this talk. And I'd like to end this talk with one last example where we actually have all 4 things: promotion, rowmotion, rotation, and webs. So I'll start with something that looks very similar to our beginning slide, except you'll notice a few important differences. Namely, this is not a standard Young tableau. This is an increasing tableau. And so we can have more than one of a number. So notice there are 2 3s, 2 10s, etc. So in 2014, Pachenik showed that 2-row rectangular increasing tableau. That's my doorbell. Sorry. Anyway, 2-row tableau, increasing tableau that are packed. So all the numbers from 1 up to some highest number are represented. These are counted by the d small Schroeder number. And there is a formula for these things. I just didn't feel like writing it out because it's sort of immediately going to become irrelevant for us. Oh, and it also looks like I spelled Schroeder differently. Okay, we'll fix that later. Anyway, so we're going to immediately move to increasing tableau of where we are allowing gaps. So notice there's no 2s in this increasing tableau, and that's okay. So they're not counted by the Schroeder numbers anymore, but they end up being counted by McMahon's box formula and relating to plane partitions. So that's cool. And so I want to show you one of these bijections. So again, we have order ideals, some tableau, and now this is a non-crossing partition. So this bijection to non-crossing partitions goes very similarly to what we saw with the non-crossing matchings. Numbers that are only in the top row end up being the smallest number in their block. Numbers that are in both the top and bottom row are a middle number in their block. And numbers that are only in the bottom row are the largest number in their block. And then the numbers that don't appear in the increasing tableau are just singletons in the non-crossing partition. So that's why we can move to this packed case because it just puts singletons in there, which end up rotating with respect to promotion. So again, if you have an action that looks obvious on one of the things that are in bijection with each other, you should ask what's going on with the other ones. So we can rotate a non-crossing partition. And as it turns out, we can do promotion to an increasing tableau, and that will be the right action on those objects. So how do you do promotion on an increasing tableau? Well, Pechenik introduced K promotion using K Takan, which was first studied by Yang and Thomas, or Thomas and Yang. And so what happens is you delete the 1, and now you sort of have a tie. The 2 3s don't really know which one should go into that box, so both of them do. And now you have 2 holes, and there's only 1 6, and so the 6 just splits apart and goes into those 2 boxes. And then sometimes sliding happens as usual, but then when you get to the end, you subtract 1 from everything. Now, as before, that's not my favorite way of looking at this action. So I'm actually going to change the example here so that it shows up better for this definition. But with Pechenik and Dilks, we introduced K Bender-Knuth involutions, which act similarly to standard Young tableau. First, we look at 1s and 2s, and then 2s and 3s, but there aren't any 3s here. So the 2 just turns into a 3. And now we look at the 3s and 4s, but the question that we're asking here is different. We're not swapping things. We are either incrementing, we're individually looking at each entry and incrementing and or decrementing it. So it turns out this 3 and 4 up here are kind of stuck, but that 4 down there can turn into a 3, so it does. And then sometimes it just looks like a swap like before. And sometimes it does something slightly different. So anyway, so that's how K promotion works using K Bender-Knuth involutions. And all of this is related to K theory of the Grassmannian, but I'm not going to get into that. So anyway, what Pechenik showed in that 2014 paper is that K promotion on 2 by D increasing tableau with a certain cap on the number of entries and rotation on non-crossing partitions of a certain number of elements correspond. So that gives us a good reason why K promotion has a nice order. And then basically he proved this for the packed case, but you can kind of throw in these singletons and these gaps and it doesn't really make any difference. So I stated it in a higher level of generality. Meanwhile, Nathan Williams and I were looking at Rowmotion on this product of 3 chains where one of the chains is of size 2. And we were able to relate that to rotation of those same non-crossing partitions. And then only later, when we resolved this packed and singleton thing, did we see the connection between the 2. Namely that K promotion on 2-row tableau is the same as toggling a product of 3 chains from back to front, sort of by hyperplanes. So I'll just show you how that works. So you saw those hyperplanes coming from back to front in that product of chains. So that's what was able, and then through the magic of the toggle group, we were able to relate that to Rowmotion, which was toggling from top to bottom. So we have this complete picture with Rowmotion and K promotion and rotation. Then the last question is, what about webs? So to tell you the web story with non-crossing partitions, first I want to show you another bijection. Okay, so this bijection, so we've already seen this bijection on the right between an increasing tableau and a non-crossing partition, and this time we're going to say no singletons are allowed. Now I want to show you this bijection on the left between the increasing tableau and a pennant-shaped standard Young tableau. So this is sort of like a flagpole. You have 1 column that's as long as you want, and then 2 rows that are as long as you want. And the way the bijection goes is we look at the numbers that are only in the top row, and those were the smallest number in their block over here. And then on the left, those are the numbers in the top row of the standard Young tableau, so that's easy. And now we look at the numbers that are in both the top and the bottom row. And we do something a little bit weird. We just look 1 number to the right of everything in the bottom row. So these pink numbers, and those are what go in the flagpole of our standard Young tableau. And then everything else that's left in the bottom row is what goes in the second row of the standard Young tableau. So slightly trickier than the other bijections I've shown you, but not too bad. Okay, and so now that we have standard Young tableau, now we can talk about spec modules and webs. So there's the spec module associated with standard Young tableau of this shape. And we might want a web basis because it has those nice properties. So this was in work of Brendan Rhodes and then more recent work of Rhodes with Jesse Kim. And then in a recent paper, joint work with Petrius and Pechenik, we all showed that non-crossing partitions index a basis for this spec module. And since this is a non-crossing partition, the long cycle is going to act by rotation. So several different perspectives on this problem. In our proof, we defined an explicit polynomial for each non-crossing partition and show that this is a basis. And so I wanted to show you how those polynomials work in my remaining 2 minutes. So here is a not a non-crossing, but here's a set partition. And we're going to turn this set partition into a polynomial. And what we do is we form a bunch of different tableaux with the elements of each part in the columns. And then the first 2 rows should be filled. And then rows 3 through the end should have only one box in them. And then each of these columns indexes one of these determinants. Just by the row index is just what row are these things in, and the column index is what numbers do they have. And then there's some inversion number associated with this tableau. So the idea is we take all of the different jellyfish tableau associated to this set partition, and we take a signed sum of their associated determinants. And like that giant polynomial is the polynomial that's the basis element associated to the set partition. And then the theorem is that it's not the crossing ones, right? It's the non-crossing ones that give us the basis. And one thing that really helps in proving this is this 5-term recurrence that I just gave you in picture form here. But what it really means is the polynomial associated with each thing, each of those 3 things summed together on the left equals the sum of those 2 polynomials on the right. And this specializes to an uncrossing rule. And so that's what helps to show that the non-crossing things are a basis. All right, and so there's our full picture with row motion, pro motion, rotation, and webs. And thanks so much for listening.